Hello, in this video we're going to talk about a novel approach based on aspect-oriented programming which aims to make configurable technologies such as FPGAs more accessible to users while allowing this technology to be fully exploited. One of the most innovative features about our approach is that we use aspects not only to guide and control all stages of the design flow, but also to capture and reuse best practices and user knowledge. Here we show the Lara design flow. The main inputs of the design flow are the application sources and a set of aspect descriptions which controls the tools. The Lara sources are converted to an intermediate representation called aspect_ir. The design flow has a set of weavers which are executed in sequence, receiving the source and the aspect_ir as inputs, and passing the woven versions along to the next weaver. In addition, information produced by profilers and runtime reports can be fed back to the design space exploration tool to refine the strategy and run the design flow until a particular goal is met. The Lara aspect language, which we designed in this project, can capture a number of schemes that can be a part of a strategy to achieve a particular non-functional requirement, such as performance, safety, fault tolerance, and energy efficiency. All these schemes, such as code transforms and mapping, are achieved using Lara's single weaving mechanism. So here is what the Lara strategy looks like. On the top left-hand side, we have an aspect definition that invokes low-level aspects. These low-level aspects, shown on the right, perform a sequence of compiler transformations which have been known to accelerate kernels mapped to FPGAs.
This aspect causes the insertion of a call to a profiling function, after each assigned to variables inside the grid iterate function named ACC or whose name starts with left or right, as well as the required header file before the grid iterate and the main functions, and a call to a function for printing the final report. As expected, the call to the function that prints the final report was inserted in the main function. The include directive was inserted before the main and grid iterate functions, and profiling is performed only to the selected variables. Let's now see the execution of the weave application. As expected, the weave application printed extra information related with the range of values used by each of the selected variables. This aspect selects all functions and maps them to Virtex 5 FPGA if their estimated cost on the FPGA is lower than on the PowerPC processor. 18 functions have lower cost on the FPGA and are therefore going to be mapped to the FPGA. The application is partitioned into code for the PowerPC processor, the Virtex 5 FPGA, code for initialization of the Molan architecture, the PowerPC stub, and the Virtex 5 proxy. This aspect instructs the compilation toolchain to enroll the innermost loop of the grid iterate function with an enroll factor of 4, and map the grid iterate function to Virtex 5 FPGA. The application synthesis step creates a VHDL description from the enrolled grid iterate function. As expected, from enrolling with a factor of 4, the loop iteration variable k is incremented 4 times instead of 1.
So currently, much of the design process is manual, where developers mix the implementation of non-functional requirements with the main functionality, which leads to low productivity and low maintainability. If you want to move beyond current design practices with our weaving approach, where the main functionality and code related to non-functional requirements are maintained separately and then combined by an automatic weaving process. One of the benefits of our approach is that a weaver can automatically derive custom designs based on aspect descriptions that capture specific non-functional requirements. By keeping the functional and non-functional descriptions separate, it's easier to maintain them according to their life cycle. Another benefit of Lara is that aspects can be reused if they are generic enough to target applications from the same domain, thus improving productivity as well as maintainability. Aspects in Lara can also be parameterizable, where results from profilers and tool reports can be used to generate more efficient designs using an iterative process. So in conclusion, in this project we have designed an aspect-oriented language where complex schemes such as code optimizations can be implemented to realize non-functional requirements. By capturing non-functional requirements such as speed and power, the Lara language is capable of capturing best practices and user knowledge.